Welcome back to Calculus 1 again, and this time we are going to continue the study of linear approximation. And remember, the linear approximation really comes from the definition of the derivative. Derivative, it is the limit of difference quotient. Indeed, this is the slope of the tangent line, and which indeed can be approximated very well by the slope of a secant line if the other point chosen is really close to that given point. And so according to the approximation of the derivative using the slope of the secant, we get the linear approximation formula right here. It might be harder to understand those notations and how we make this linear approximation useful. So we introduced one example. It is to approximate square root of 9.1. And we did this in the last video. And this time, I'm thinking not to repeat what I did, but anyway, let's start with a new example. Should be very similar. This time, we are considering it is to find the linear approximation of q root of 8.1, q root of 8.1. And still, well, I suppose we know, in this case, the function we consider must be the q root, right? The third root here. So I chose the function as the third root of x. And then according to the linear approximation formula, actually somewhat I think I miss anything here? Okay. Yeah, actually I guess I got an extra line here. Mostly I use copy and paste a lot on my notes. I guess this part of the line is really not needed. Okay. After you choose this function, because it's a q root of 8.1, so the function chosen here, it is the third root, the q root. And according to the approximation formula, we do need to have the two notations x and h. Because q root of 8.1, it's a little harder to figure out, but I do know the third root of 8, which is 2. And also, I say it should be easier to understand. 8.1 is really close to 8. So my choice of x is 8, because I can handle the third root of 8 perfectly. And the difference or the gap between 8 and 8.1, that's 0.1 h. So this is the linear approximation formula. F of x plus h should be, I think you still use approximation notation here. It is approximately. Okay, f of x plus h times f prime of x. F of x, like we did, it is the q root of x, the third root of x. H is 0.1. F prime, as we calculated right here, 1 over 3 times the q root of x squared. By the way, the q root of x squared, it can be considered the q root of x with parentheses squared. It can be done either way, okay. So in this case, it might be just easier if we take the q root of 8 first, and then that's 2 squared, that's 4. Okay. Or you simply can do 8 squared first, 64, q root of 64, that's 4. So this part of fraction is 1/12. 0.1 times 1/12, and then add to the third root of 8. So overall, I got the result as 2.00833. And I say this is a very good approximation for the q root of 8.1. And also, if you are watching this video, well, do give a try. Use your calculator to see if you are convinced this is a reasonable approximation. It should be close to what you may get from the calculator. Okay, so this is about the linear approximation part for, well, this is one application of the derivative. Otherwise, like we did the example previously, square root of 9.1, we really have to use calculate. and then cube root of 8.1, and then we're going to use calculator again. And now we figured out somewhat we can do something like a calculator, and eventually we can make the calculator to work. Okay, this is essentially the idea how calculator works. Linear approximation. And how about let's take a look another topic of the section. Section 4.2 has two topics: linear approximation and differentials. They are all about derivatives. So let's take a quick look about differentials. Hopefully differentials are not as complicated as linear approximation, but make sure you do the writing correctly and completely. Okay, so derivative, differentials, linear approximations, they are all about derivatives. F prime y is a function of x, so f prime simply can be written as y prime. And also we did say sometimes we do prefer this long fashion notation, ddx notation, dy dx, because it says clearly we are considering the derivative of y with respect to variable x. Okay, y is a function of x. And in general, you really should say dy dx is not separable, because remember, derivative, it is not only a quotient, it is a limited difference quotient. So this way of writing, in general, it is not separable. But anyway, mathematically, we can separate the dy dx. So I want to tell you right now, dy dx, indeed are the differentials. Certainly, dy, it is differential y, dx, it is differential x. Besides, those two differentials are related. And so specifically, dy, it is y prime times dx, or simply it is y is a function of x, the derivative function times x. Derivative function times dx. Okay, dy, it is the derivative function times dx. It is very important to note when you write a differential, usually you need to have dx in the end. You need to have dx in the end. Okay, so let's take a look about the examples on the textbook. It's all about computing differentials, find the different differentials. This is example 4.8 from the textbook. There are two parts, part A and part B. dy, y is x squared plus 2x. So dy, it is y prime times dx. So dy, y prime, it is 2x plus 2. According to dy, it is 2x plus 2 times dx. Do consider this times, okay? Okay, when you consider multiplication, well, you cannot drop any part. So this dx, it just stays there. And similarly for part B, dy, it is y prime times dx, which is negative sine x. And actually, I really have to correct myself. Negative sine x, it is derivative y prime. dy, it is y prime times dx. This is part of what I want to correct. Now this should be the correct answer. dy, it is always something about dx, something times dx. Okay, a differential will have to compare with another differential. Okay, usually you don't have dy equals something, well, without another differential. Dy will have to be something about x and times dx. And one more example about differential, find the dy. Dy, it is differential. Okay, dy, it is dy is y prime times dx, right? Besides, you think about this notation, even though I said it many times, dy dx is not separable. But anyway, I guess to help understand or memorize the way how we write dy, you consider you can multiply dx to both sides. So dy is y prime times dx. And now dy dx each has a name differential. dy it is differential of y, dx is differential of x. So in this case, y equals e to the x squared. And differential, remember I said in order to understand the differential, you do need to know derivative rules very well, because first thing you need to do here, it is just to calculate the derivative. So this time it is about the exponential function with the chain rule. So I got the derivative as 2x times e to the x squared dx. Don't forget the dx in the end. Without the dx in the end, simply it is just not correct. Dy will have to be something of a function of x times dx. Without the dx in the end, simply it is not correct. Okay. And so this is what I wrote here. Note for each dy, there is dx in the end. It should be good. And also, I think this time we have mostly in calculus. It is the study of limits and the derivatives and the integrals. And also, so far, mostly we are doing derivatives. And really, the real reason for this part we consider differentials because we are moving to the discussion of integrals. And to write the integral notation, we use dx in the end. And also, hopefully, if you understand it clearly, with dx in the end, it is differential. So in the writing of integral, we also have dx in the end. You cannot drop that. Okay, so then if you really want to make sense what a differential is, differential it is about derivatives, but anyway, it is more like the term of difference. Differential should be considered as a very tiny change. Differential it is a very tiny change, infinitesimal change. That's a differential. So this is what I said. Compared to derivative, differential, it is more like a difference. Differential, it is more like a difference. So this is discussion of section 4.2, linear approximation and differentials. Hey, thank you for watching. See you next time.